Have you ever really stopped to wonder what's going on inside your computer? Like right now. Well, today we're going to pop the hood and see how it all really works. And you might be surprised to find out it's a lot like a team working together. You've got a car, an engine, a brain, and even a huge workspace.
So, let's kick things off with a question. You've heard of your operating system, right? Windows, Mac OS, that kind of thing. But have you ever heard the word kernel? Now, are they the same thing? What do you think?
The answer is nope, not quite. And believe it or not, this one little difference is the key to understanding, well, pretty much everything about how your computer works.
All right, so to make this super clear, let's use an analogy that I think you'll get right away. A car and its engine.
So here's the deal. The operating system is the entire car. It's the shiny paint, the comfy seats, the steering wheel, the radio, everything you see and touch. But the kernel, well, that's the engine. It's tucked away under the hood, but it's the powerhouse doing all the really important work that makes the whole thing go.
So the operating system, our car, is what adds all of the user-friendly stuff we just expect nowadays. The graphical interfaces with all the windows and buttons you click, the apps that are already there when you turn it on, and those easy setup wizards. A perfect example of this is Ubuntu. It took the super powerful Linux kernel and basically built a beautiful, easy-to-use car around it so that anybody could drive it, not just the expert mechanics. Meanwhile, that engine, the kernel, is working non-stop in the background. It's managing things like your printer and your mouse, it's figuring out how to use the computer's memory, and it's basically playing traffic cop, deciding which programs get to use the computer's brain. And get this for a fun fact. Linus Torvalds, the guy who actually created Linux, he used to run just the raw kernel on his machine. No car, just a pure raw engine.
Okay, so we've met the engine and its manager. Now let's talk about the real brain of the operation, the CPU. This is where the magic really happens.
The CPU, or Central Processing Unit, is where everything, and I mean everything, actually runs. Every click, every character you type, every single thing happening in your favorite game, it's all being processed right here. It's all happening in real time, which means for the CPU, speed is literally everything. But that brings up a really good question. If the CPU is so incredibly fast, how does it deal with the fact that the information it needs is often stored in memory, which, in computer terms, is like a million miles away and super slow to get to? How does it stay so fast? Well, it uses a super clever trick called a cache. Think about it like you're doing homework. The fastest possible way to get writing is to have a pencil already in your hand, right? That's your L1 cache. It's instant. Almost as fast as having a pencil right there on your desk. That's your L2 cache. Still pretty quick is a pencil in your desk drawer. That's L3. But having to get up, walk to another room, and find a pencil, that takes a while. That's your RAM. So the CPU is always trying to guess what you'll need next and keep those pencils as close as possible. And CPUs themselves have gotten a whole lot smarter. Back in the day, a computer had a single-core CPU. It was like a grocery store with only one checkout line. Every single program had to get in line and wait its turn. But today we have multi-core CPUs, which is like having a bunch of checkout lines open all at once. Different programs can be processed at the exact same time, which is why everything feels so much faster now. But this actually creates a brand new problem. What happens if two of those checkout lines, or two different CPU cores, both need the exact same piece of information at the same time? What if one of them changes it? Well, to stop things from getting messy, the computer basically has to call a quick timeout. It spends a tiny fraction of a second making sure that every single core has the most up-to-date, correct information. It's a trade-off, right? You get all this amazing speed from having multiple workers, but you have to pay a small price in time just to keep them all on the same page. So we know the CPU is the brain, but how do we actually talk to it? Well, it turns out different types of computer brains speak slightly different languages. You've basically got two main families. First, there are RISC chips, the kind you find in your phone or in Apple's new M-series laptops. They are all about being power efficient. They use really simple instructions and just sip power like they're drinking through a tiny straw. Then you've got CISC chips, which you'll find in big, powerful gaming PCs. They can handle way more complex instructions all at once, but they guzzle power like they're chugging from a giant cup. This is the exact reason your phone battery lasts all day, but a powerful gaming laptop usually needs to stay plugged in. But here's the thing. Deep down, Both of those types of chips only understand one single language, machine code. You can think of it as their secret native language. So when a software developer writes a program in a language a human can read, a special process called compiling has to translate it, word for word, into that secret machine code the CPU can finally understand. And this leads to a really interesting choice for programmers. They can use a compiled language like C++. This translates their code directly into that secret machine code, making it super, super fast. But it only works on one specific type of CPU. Or they can use an interpreted language like Python. Python code runs on top of another program that acts like a live translator. It's a little bit slower, but it means the same Python program can run on almost any computer out there. Okay, we've covered the engine and the brain. Now let's talk about the computer's short-term memory, its main workspace, which is called RAM. Hey, remember our homework analogy? Getting data from RAM was like having a walk to a whole other room. Well, here's another way to think about it. Every time the CPU needs to get something from RAM, it's like making a long-distance phone call. Making 1 or 2 calls? No big deal. But what if your program needs to make hundreds or even thousands of these calls, and each one takes time? Well, you're going to be spending a lot of your time just waiting. And this is exactly why keeping important data in that super close cache is such a game changer. The R in RAM stands for random access. And the absolute best way to understand what that means is to think about old VHS tapes. If you wanted to get to your favorite scene in a movie, you had to physically hit the fast forward or rewind button and wait. That's called sequential access. RAM is completely different. It's like the menu on a streaming service. You can just click and instantly teleport to any scene you want. No waiting, no fast forwarding, just random instant access. It's awesome. So we've looked at the kernel, the CPU, the cache, the RAM. We've seen all the individual players. For our last section, let's just zoom out and see how this incredible all-star team works together. So let's recap our all-star team one last time. You've got the kernel, who is the team manager, directing everyone and telling them what to do. You've got the CPU, the brain of the whole operation, doing all the actual thinking. Then you have the cache, which is the clever shortcut, always keeping important stuff nearby. And finally, you've got the RAM, which is the giant workspace where all the projects are laid out and ready to go. You know, it's pretty mind-blowing when you really stop to think about it. Every single time you click your mouse, or watch a video, or play a game, all of these parts, the manager, the brain, the shortcut, and the workspace, are all working together in perfect harmony, thousands of times a second, just to make your digital world come to life. So at the end of the day, your computer isn't some magic box. It's an amazing, finely tuned machine built on decades and decades of brilliant ideas. So now that you've had a peek under the hood and you've seen how the engine, the brain, and all these parts work together, what are you going to get curious about next?